Hello. In this video, we'll talk about disjoint events in probability and how we can use Venn diagrams to visualize events that are disjoint or not. So let's start with the definition. So two events are disjoint if they have no outcomes in common. Sometimes this is termed mutually exclusive. So let me give an example. Again, I want to kind of use this example of rolling a fair die where our outcomes are 1, 2, 3, 4, 5, and 6. Visual aid here. And maybe we define an event E as 1 and 2, and the event F as 4, 5, and 6. And I'm going to define an event G as 2, 4, and 6. So I notice that event E and F have no elements in common. This has a 1 and a 2. Here's 4, 5, and 6. So E and F are disjoint. But E and G share the 2, and F and G share 4 and 6. So E and G are not disjoint. They have a 2 in common. And I don't mean two things, I mean the actual element 2. And F and G are not disjoint. They have the elements 4 and 6 in common. So a tool that we sometimes use in probability is called a Venn diagram. And the way this works, we start with usually a rectangle that's kind of acts as a frame. And this represents our entire sample space. So I'm going to put a little S up here in the corner. And to make a collection within S, an event, I'll usually use a circle or some similar shape. And so maybe this is event E. So the way that I've defined this up here, E has the elements 1 and 2 in it. And elsewhere in my sample space, I have another collection, which I'm calling F, which has the elements 4, 5, and 6. So that's F. And so these have nothing in common. So notice I've purposefully drew them so that there's no overlap. So when you want to indicate disjoint events in a Venn diagram, we'll draw shapes that don't overlap. Now, if I wanted to show that they are not disjoint, so for instance, here, this is G, and notice that G has overlap with E, because they both share this element 2, and G has something in common with F, the elements 4 and 6. So this space here is the common ground for G and F, and this space is the overlap, or the common ground for E and G. So E and F are disjoint, but E and G are not, nor are G and F. So the notion of disjoint comes in handy if we want to know the probability of one thing or another happening. So for instance, let's say we want to know the probability of E or F. So this means that you could have an outcome from one or the other of these. So if you're thinking about how to define this, we can actually list the elements that are in one or the other or both. So that would be the elements 1, 2, those are the elements from E, and 4, 5, and 6. Those are the elements from F. So this set, this collection, this new collection I've made, represents E or F. So how can we get the probability of E or F? Well, in this case, since I was able to just list the possibilities, and I know how many things are in the sample space, I can use the classical method and say that that's 5 out of 6, because these are all equally likely. But another option, the probability of E or F, is the probability of E plus the probability of F. Now this is true whenever E and F are disjoint or mutually exclusive. In fact, we call this the addition rule for disjoint events. Now, if you have events that are not disjoint, we'll run into an issue, but it's easy to fix. So remember that we have F, which we've defined as 4, 5, and 6, and G I defined as 2, 4, 6. So let's say that we want the probability of F or G. I may start by adding the probabilities. Probability of F plus the probability of G. Notice that there were 6 outcomes. F contains 3 of them, so that's 3 out of 6. The same for G, it has 3 out of the 6 possibilities. 3 out of 6. If I add those together, I would get 6 out of 6, which is 1. So it looks like if I roll a die, there's a 100% chance that either F or G will happen. But I know that's not true because neither of these sets contains a 1 or a 3. And certainly that is a possibility on the roll of a die. So what's the problem here? When I add these two probabilities together, 3, 6, and 3, 6, basically I'm double counting some of the outcomes. I'm counting the 4 and a 6 as a possibility in F, and again as a possibility here in this 3, 6. So the way that we correct for that is to subtract off the overlap. So for the probability of F or G, I'll take the probability of F plus the probability of G, and then subtract off the probability of F and G. So F and G, this is the set of elements that are shared by F and G. So there were 2 items in this, so I'll take 3, 6 plus 3, 6, but I'll subtract off 2, 6. And so this gives me 4, 6, which reduces to 2/3. Now, remember F or G, this set is the collection of things that are in one or the other. So 4, 5, 6, 2, 4, and 6. So these were the elements in F, and these were the elements in G. But notice the 4 repeats here, and there aren't 2 different 4s. When you roll a die, a 4 is a 4, and there aren't 2 different 6s. There's just 1 6 on a die. So really, when I want to create the set F or G, it just has 4 things, 4 of the possibilities out of the 6. So that makes sense that we're getting an answer 4, 6 that reduces down to 2/3. So to sum, when you want to answer an OR question in probability, you'll have 2 choices. So if I'll say E and F are disjoint, then we can say the probability of E or F equals the probability of E plus the probability of F. And if they're not, or if we don't know, we have, I'll just say, well, actually I could say otherwise or anytime, and I'll explain why in just a minute. If you want the probability of E or F, we'll take the probability of E, add the probability of F, and then subtract the probability of E and F. Now the reason I say that this would work anytime, let's say that P and E are in fact disjoint. So remember what disjoint means. That means E and F have nothing in common. So the probability of E and F, so this precisely means what they do have in common. Well, if they have nothing in common, this is empty, so the probability is 0. So when these are disjoint, actually this term becomes 0, and we end up back over here with this rule. Now, so this is safe to use anytime. In fact, we call this the general addition rule. Alright, so that is a discussion of disjoint events, Venn diagrams, and our two addition rules. I'll be back with another video to add some more probability rules. I hope you'll join me.